harmonic. What do you mean harmonic? Means either cosine or sine. That's mean harmonic. Okay, if you look at this, look at harmonic. U1, let me explain this a little bit so that you won't be confused. E1, Ei omega t, in theory, that means E1 is a constant, is a vector, that's constant value, times cosine omega t plus I sine omega t, right? Okay. Now, if you look at the I omega t means cosine omega t plus I sine omega t. That's my U. That's my U1. Now, my question is, do we really have this kind of input? Do we really have this kind of input? Yes? No? No? And why I use I omega t? There's no such input has an imaginary part. Can you see, can you imagine that any complex input, what does that mean? There's no meaning. All right, okay, let me explain to you. This is just for mathematical convenience. This is additional term. This is my additional term. My harmonic function term is really cosine omega t. U1 cosine omega t. So I really looking at U1 equal to U1 cosine omega t. Let me change a better one. I'm really looking at U1 equal to U1 cosine omega t. That is the harmonic function I'm really looking at. Omega can be any frequencies. But I purposely add this one here so that I can solve this equation much easier if I use exponential. Understand that? So this is just for mathematical convenience. After you solve it, you have to be careful for the solution because you have something which is not a real sense. Your solution has something not real. So you have to take the imaginary part of your solution out. Right? So I do this. This is just for my mathematical convenience because it's easier for me to solve this if I say W equal to omega and W1, W2, also exponential I omega t. This W or W here. The W is W1 t equal W1 e I omega t, W2 e I omega t, and we write a vector form like this, and we got W is W1 and W2. If I do this is my steady state response. If I sub into it, then I got this matrix because ei omega t in this side and left hand side, right hand side, they are cancelled. Right? Think about it. If I use a cosine omega t, can I write this kind of symbol form? No. But I do have a penalty because I do have the I here. Right? But don't worry about it because after you get solutions, you know that the solution has to be real. So that imaginary part is come from that I. We can take them out. Understand now? So sometimes this is some mathematical tricks. I can understand. But in your system, you really don't have that. Don't have I. Okay. Now, this is my steady state response subject to harmonics of excitations. So what I write is, then I have an I here, and if I sub in this E I omega t in it, then I got these equations. And then I gotta solve the minus 1 here. So I add all them together, and there's a minus 1 here. Then I do this. I call this is Z11 omega. Alright, I call Z12 omega is this term. I redefine this because it looks very complicated. Then I do this, and then I can solve it Z11 omega, Z22 omega, minus Z12 omega, Z21 omega. Then there's a matrix here. That matrix is the Z11 becomes Z22 because that's metric inverse. That becomes this. All right. My message for this slide is that. Okay, is this. So my W1 equal to a this long form, this Z11 Z22 omega divided by Z11 omega, Z22 omega, minus Z12 omega, Z21 omega, and then E1 over M1. W2 equal to minus Z12 omega divided by the same denominator. So this, the same denominator. Alright. This. Again, we look at this one. This is my displacement. This is my displacement. This is my force, E1. That's my amplitude. If I move E1, omega 1, divided E1, that's my frequent response. So my frequent response is defined like this. So if I do this, then this the first state response is this. My second state response is this. This all depends on omega. If your omega changing, then your response is changing. Your harmonics are like your earthquake frequency changing, then your response will be different. So depend on your input frequencies. All right. I will repeat this definition next week or a little bit. But at this moment, now I introduce the steady state response because this is the one everybody use to tune the TMD. Right? That's the way to tune it. Well, I mean, commercially, everybody using this. But academically, you can have a different way to do it. Okay. Well, our time's up, and then I forgot to also ask you if you have any question about the homework. And I didn't really try to also talk about homework, but I time. And this homework, I hope you don't have any questions. If you do, you can put in the web, or you can ask the teaching assistant or and so on. Okay? Any questions?
Yeah, good.
You do? About these questions? Homework?
Or the second one?
The second one?
Yeah.
Solve the different differential equation of motions,
Yeah.
right? For x in terms of the following term. I'm talking about steady state solution. Yeah, steady state response. Mean non-homogeneous solution.
Yeah, but also terms are cosine sine.
Yeah, I know. That's why I introduced this way. You can do this way too.
What
If
do
you
you
like.
choose that? Okay.
Well, why not? You can write? Oh, well, I give you some hint. Otherwise, you can just sum into it, and then you can assume x equal to a1 cosine omega t plus b1 sine omega t, and then solve that. That's the conventional way.
very big.
Right? And that's, you can do that too. That's a typical differential equation way to solve. You can just read your ODE, you can read some book, ODE, and know how to do it. Alright, just to give you some exercise. Alright, see you next time.